Hello everyone, my name is Chih-Chun. I'm a recent graduate student from the University of Toronto Institute of Aerospace Studies, and today I'm going to present model of UAV and downwash for multi-UAV path planning. So downwash is the force generated underneath the rotors due to the large volume of airflow, and the UAV underneath can lose stability or drop altitude. It is an issue for real UAV flying in a 3D dense environment because it can easily cause collisions. To prevent collisions, it is important to find out how significant the downwash effect can be. And from the path planning point of view, the downwash problem can be solved by modeling the UAVs to cylinders instead of spheres. This would enlarge the vertical separation between UAVs. So the objective of this research is to model the downwash effect to figure out how significant the downwash impact can be, and to prove that in cylindrical models do prevent chaos due to downwash by simulating two path planning algorithms. To model the downwash force, there are 4 steps. The first step is to obtain the thrust force by using the equation of motion with an input of acceleration. The second step is to use the momentum theory to convert the thrust per rotor to the airflow velocity underneath the rotor. The bottom UAV that suffers from the downwash will be a distance away from the top UAV, which the distance in this figure is represented in Z. So the third step is to obtain the airflow velocity that is a distance away from the rotor by using the jet flow concept. And the fourth step is to convert the airflow velocity to the downwash force, which is the force that the bottom UAV will suffer. Since the downwash airflow direction tells us the UAV does, the downwash model will also need to consider the UAV orientation. First, we need to obtain the distance between the two UAVs, and in equations here we use UAV1 and UAV2. If it is in the east-north-up frame, then UAV2 will suffer from the downwash if the Z component of the distance differences is larger than 0, and the horizontal distance differences is within the diameter of the UAV. And this equation shown in the last line shows the direction and magnitude of the downwash acceleration that UAV2 will suffer from the inertial frame point of view. When the downwash airflow does not hit the center of mass of the UAV, there would exist the downwash torque. The angular acceleration caused by this torque can be determined by a simple physics equation shown in the second line here, and it can be converted to the angular roll or pitch acceleration depending on where the airflow hits the surface of the bottom UAV. To test on how the cylindrical models can prevent the collisions caused by the downwash effect, 2 path planning algorithms are introduced in this research. The first one is a flocking algorithm. It is a force-based algorithm that consists of 2 parts: the navigational feedback and the repulsive force. The navigational feedback is the force that leads the UAVs to their individual goals, and the repulsive force is the force that prevents collision avoidance between UAVs. And the second algorithm is the optimal reciprocal collision avoidance algorithm, also known as ORCAR. It is It first obtains a set of velocities that would cause inter-UAV collision before a time horizon, and according to the set of velocities, it then obtains a all-car half-prime, and then based on the optimal velocity of the UAV, it gets the new velocity. So all-car is a velocity-based algorithm. Both of these algorithms have been modified a bit to convert the spherical model to cylindrical model. We simulate the downwash model by considering the worst case, where one UAV is hovering and another UAV flying past from right above it. This is the worst case because it can maximize the amount of time that the bottom UAV suffers from the downwash. And here we consider three cases. The first case only considers the vertical downwash force. The second case adds on the tilted downwash airflow. The third case further considers the downwash torque. And the figures shown here are the position of the bottom UAVs. And here we can see that the UAV in the first case only suffers from the altitude drop, and UAVs in the second and third cases also suffers from the horizontal movements. The altitude drop at most in the first case because horizontal movement of the UAV can reduce the time that the UAV suffers from the downwash. Python simulation over 100 runs are done to test for the performance of the cylindrical models of the blocking algorithm and the all-car algorithm under effective downwash effects. To create a 3D dense environment, we have 10 UAVs hovering inside a 2x2x1 space, and another 10 UAVs traveling from one side of the space to another side. As we can see from the chart, for both path planning algorithms, the cylindrical model performs a higher success rate than the spherical model. And here the success rate is the cases where the UAVs did not collide or stuck, and the UAVs successfully travel from their initial to final locations. And that's it for my presentation. Thank you.